Thank you, Professor Wagih, for the introduction, and thank you for being here on time after the lunch session. So my name is Mahmoud Wagih. I'm from the University of Glasgow in the UK, and thanks to the track chairs for inviting me to give this talk at the start of the wireless track here at FLEPS. Good to be back at FLEPS after several years from taking a break due to COVID and various reasons. So here we are talking about sustainable electronics, wireless electronics, and why the two need to come together, and why do we need to have a wireless track at FLEPS, for example. So what is wireless? We are in a flexible electronics conference, so I'm not going to assume that everyone here knows wireless, although I see a lot of familiar faces in the audience who work in this area. This is a generic diagram of what the Internet of Things might be, or what smart things are: sensors, physical interfaces, intelligence somewhere, and then user interfaces. And really, wireless technologies are these arrows. Currently, the only role of wireless technologies is to get information from one point to the other. Wireless technologies are very good at doing this. They're very good at generating value and doing their job in just getting data from one point to the other. But we want to do more with wireless electronics. So let's zoom in. That's what a typical wireless circuit looks like. Lots of components, signal generation, signal reception, lots of frequency multiplications and components that we don't need to look at too much right now from the context of sensing, but very essential for communication. And if you want to look at specifically what's antenna engineering, we heard a lot about flexible antennas, is that final block of a system. Yet, if you go on IEEE Explore, you'll find that antennas are one of the highest searched for keywords of all keywords in IEEE Explore, partially because of communication, partially because of antennas and wireless technologies. So even though it looks like a tiny portion of a system inside a bigger system, it's still a very large and important research field, which is why we're asking the question of what can we do more with antennas? What can we do more with particularly flexible and printable antennas? So what can we do as a wireless community, as an RF technologies to the flexible printed electronics community? In my presentation today, I will take standard electronic components that have been fabricated using flexible or large area processors, inductors, resistors, and capacitors, make them into antennas, combine them together into systems, run them at a very high frequency, starting from several megahertz into several gigahertz, see how we can use those to make A, sensors, B, power and electronic devices, and finally, how they could enable us to have sustainable electronics, how they could enable recycling, and what is the real sustainability impact of these systems. And of course, looking at it from the other point of view is what can we take from flexible electronics? What can we take from low energy manufacturing, from large area manufacturing to give back to standard wireless networks so that we can make them more sustainable or potentially more efficient? So let's start with sensors. And one of the best ways to sense with high frequency systems, with wireless systems, is to just harness the existing physical properties of materials. Everything around us has a permittivity or a conductivity. And if we look at the changes in these two parameters, basically things coming into interaction with our devices, we can have very effective sensors which could outperform the traditional sensing approaches. Now, before I go further and talk about what are we actually building, I need to add a slide on what is RF sensing, because various people come in with different understanding of this, particularly because commercially, and particularly in the microwave industry, it usually means radar, which is not what I'm going to cover. In the traditional radar sense, we've got a transmitter and a receiver with one or more antennas. You send a signal into what you're trying to sense. You receive a signal that is distorted by some way. And as far as that signal and as far as your system are concerned, this is just a big lump of conductivity and permittivity that changes in space and potentially in time, which can give you understanding of speed, for example. But if you're trying to understand something more, like biomarkers or physical parameters, you start to collect a lot of data. You start to involve machine learning and AI to train something on a usually non-physical model built on lots and lots of data. That model usually works. It usually says what you expect it to say, but it sometimes can go terribly wrong. There are lots of examples of these systems going terribly wrong, one of them being the weather radars. Every time in the UK, at some point of the year, it confuses flying insects for rain. The weather will be nice and sunny, but the forecast will say it's raining simply because a block of high permittivity came into the way of the radar. It looks like a cloud. It's not a cloud. So without a physical understanding of what's going on, without systems that are designed for a specific operation environment, we can end up with a situation like this. So wireless is not the answer to all problems. What we do instead is taking the thing that we're trying to sense, perhaps our friend here in a remote environment, And we add lots of sensing devices, making use of the fact that flexible electronics could be scaled quite easily. And then we take those devices and we start to look into them as equivalent circuits. How does they interact with their environment? We could potentially load them with a functional material, or we could use their intrinsic properties. And then with that, we get a radiation profile that is unloaded. We've studied that using well-known techniques. Then we get a loaded radiation profile, again, simulated and understood potentially analytically in our practical operation environment, which gives us a physical understanding of what is going on. Usually, we try and do this without significant data processing or based on physical models. So what have people applied this to? We like our liquids because liquids come in various permittivities, so we can quite easily characterize different liquids, and most biological mediums could be traced back to liquids. More evidence of people liking liquids. We're very good at detecting moisture because it attenuates radio waves, so there are various applications of sweat, moisture sensors, fabricated using RF and large area electronics. Another example of moisture, food and oils, still moisture. Fruit ripeness, still basically water-based materials. Various approaches, so many others that have been reported, but all of these are simply capturing changes in permittivity that are occurring naturally in the environment. And as long as we understand our material, as long as it's done in a nice lab bench with a nice expensive test instrument, it all works fine. But we want to take these out of the lab, and we want to build systems that do not require one of these network analyzers, which costs tens of thousands of euros, in order to get our practical system. And there's another question. Whenever we build one of these sensors, someone comes back and says, I can do this with a multimeter. Why should I use an RF sensor? Why can't I just have an ADC, stick a multimeter into my resistive sensor, get my reading, happy days? So an example that we've done which demonstrates why you might want to have RF sensing was in detecting ice and snow accumulation for structural monitoring for smart cities or potentially environmental monitoring. And the way to do that, we need to have reliable antennas. So we started with robust textile-based antennas or flexible antennas that we took for wearable applications. They can survive a washing machine, so they can certainly go out in the field. We model them using standard antenna approaches. We model the ice as a superstrate that sets on top of the antenna, changes the permittivity in the surroundings of our antenna, and then we go out in the field and we try and replicate our simulated results. So we did something different with this example. We usually have antennas detuning, or their performance degrades, when they come in proximity with their environment. We did the opposite. We tuned our antenna to radiate in the most efficient way when it's in proximity with the ice. The antenna's gain is maximum, the antenna's matching is optimized when it has a thick ice layer, and that's why you can see with a standard RFID reader, we can detect over 10 dB of gain change when the ice loads the antenna. Now, ice is a nearly lossless material, so it's not going to cause any additional losses. It simply shifts the resonance of the antenna. So in a way, we are deliberately detuning our antenna so that it retunes when what we're trying to capture comes into its environment. And that means we can never get a false match, because it's very unlikely for anything to increase the gain of the antenna in the real world. Usually everything reduces the gain. So whenever we see an increase in the gain or improvement in the quality factor and matching, we know that it is exactly what we're trying to sense for. So we want to take this into the real world. Things worked really nicely for the ice example. So we wanted to dig deeper into the propagation modeling, understanding what happened in our surroundings. So we have a simple antenna, loop antenna buried within the soil, connected to the 2 ports of a standard network analyzer. And what we wanted to investigate in this paper was, what is the effect of polarization? Should our reader be linearly polarized? Should it be circular? What happens if things rotate and are mismatched? And also what happens if we have a line of sight or a non-line of sight link between the sensor and the reader. In line of sight, what you usually see in papers where everything is nicely aligned, we get a perfect response. The yellow part of the graph is when we add water into the soil. You can see the signal strengths dropping, perfect sensor detection, real-time response, everything what we want to see. But when we repeat the experiment across various environments, various alignment and misalignment, various orientations, we don't always get the same response that we're looking for, and results start to look quite random. For example, when things are line of sight, when things are linearly polarized, whether or not they are in the right orientation, we can more or less capture the fact that the signal drops when you apply water, which is what you would model in a standard electromagnetic simulators. Unfortunately, when things are circularly polarized or in non-line of sight, we did notice strange readings. We, in some cases, saw the gain of the antenna increasing when you add water, because the water starts to behave as the antenna, and you happen to be at a wrong angle from the antenna's original performance. So you're now getting radiation patterns shifting towards the reader, all coincidentally, all quite random, and giving you the opposite of the sensing response you want to see, which is absorption and a reduction in gain. So all I'm trying to say here is that do not expect your antennas to behave in an ideal environment. Expect random alignments, expect changes in readout direction, unless that's all controlled. And these can significantly change the sensor's response. So we need to optimize and design the antenna specifically for operating in varying environments where things are not in the alignment we designed it for. Not everything is moisture, not everything is ice. So we want to do things linking parameters like temperature, gases, and humidity, which do not directly change the permittivity or conductivity by engineered materials. So an example of this was in temperature sensing. And in order to do a temperature sensor, in this case, we built a composite. We synthesized the composite out of PDMS and varying ratios of carbon fiber. It behaves a positive temperature coefficient thermistor, which means it has an exponential increase in resistance with temperature. We heard talks earlier about percolation. When the material expands, the conductive links break, and you don't have a conductive path, and you get an exponential increase in resistance. The problem with these thermistors for tens, if not 100 years, has been they're limited in range. Once your multimeter reads an open circuit, you've lost the sensor, and you need a different sensor to read the wider temperature range. Now, that's where we started to look into taking these materials to high frequency. So we took our composite, we built antennas, microstrip circuits, microwave circuits onto these composites. At this point, our entire substrate is behaving as a sensor, so we expect high sensitivity. We excite it with an RF power. The absorption now into the substrate is modulated by temperature, because the temperature is a highly sensitive resistor to temperature. The remaining power will be radiated by our antenna, so the gain is directly modulated by what we're trying to sense for, and that gives us direct wireless readouts depending on the signal strengths or potentially the shielding effectiveness of our composite and our antenna. Why is this useful? Because when we characterize the material at DC using a standard 4-point probe or multimeter, we get a DC resistivity that increases very quickly exponentially. We lose our sensor beyond tens of degrees. Not great, but with the RF response, we are able to improve the sensing range by over 4 times. In fact, it could be increased further, but we couldn't implement that physically in the lab in terms of temperature, simply because your lossy elements, the carbon fibers, are still there. They didn't go anywhere. The conductive paths between them broken, but the lossy material are there. We can still measure the expansion of the polymer. We can still see the effect in both the resistivity and also the relative permittivity of the substrate, giving us a very wide range sensor, which can detect temperature at over 4 times wider range than your standard thermistor. Again, why are wireless technologies useful? Because when we have an antenna which can sense for things, we can directly use the gain to monitor what we're trying to sense for. So what I have here is the measurement of the radiation patterns of our antenna at room temperature. It's a very lossy device, so it's not radiating very well. Once you increase the temperature, the substrate starts to behave like a good dielectric. You get good radiation efficiency. And most importantly, because of the antenna and material co-design that we did, we got a very high sensitivity to temperature, more than 0.1 dB per degree Celsius, and also in frequency domain in terms of resonance shift. This was the highest sensitivity compared to any other temperature sensor reported, all because we used the custom material rather than repurposed an existing electronic material. Temperature is an interesting parameter, but it's not the only thing that we need to sense for. Many people have been exploring this area. There are examples for sensing humidity using conductive polymers, PSS, one of the materials that we're currently working with because it's recyclable and biocompatible. People have explored light sensing using cadmium sulfide and other materials that are usually used in light-dependent resistors, and also volatile organic compounds and gases using vaccines, graphene, and various 2D materials, including carbon nanotubes. You basically take a standard material, you load an antenna or a microwave circuit with it, you get an average sensitivity, but once you explore the design of your geometry and the material together, you can achieve the exceptional sensitivity as we've just shown. So that's all about sensing. That's all about us taking RF techniques and moving them to the IoT. But we want to do the opposite. We want to take some of our flexible electronics. We want to take our large area systems in standard wireless communication and wireless power applications and demonstrate that they can outperform the components you can buy off the shelf. An example fabrication approach, which many people are familiar with, is screen printing. Very familiar in the textile industry. Many printed t-shirts are fabricated using this approach. You pass an ink through a screen. The screen has the pattern you want. You now have conductive particles on, in this case, a polyurethane film, which allows us to apply it on virtually any fabric. We can then cure the silver, or at least pre-cure it so that it doesn't fall off from the substrate. Then we heat press it or laminate it onto virtually any textile. Regardless of roughness, the polyurethane layer will smooth it out and will give you a nice conformal layer, which maintains reasonable surface roughness for high-frequency applications. And because it's a very scalable approach, we can build multi-layer components. And many of you now will recognize that this is a capacitor. So we can start to build capacitors, potentially inductors, and more complicated structures using simple additive manufacturing and thermal lamination, which is all a very easy to implement approach in outside a clean room environment or outside a controlled lab environment. So we take a capacitor. Here you can see a cross-section of the device. We have silver, we have polyurethane, another silver layer, so metal insulator, metal topology of a capacitor. We integrate it within a standard transmission line. So now you have the capacitor built in within a transmission line. And this is very significant for RF applications because we want to control where our DC signals go, where our RF signals go. It's essential part of any RF front end where you're providing bias to an active device. But what we're doing differently with printed electronics is we think we'll achieve better power handling because it's a larger component and it's low loss. We also think in a flexible or a wearable application, it's going to be extremely reliable from a mechanical point of view because there are no rigid paths to break. We heard in various talks is that surface mismatch between rigid and flexible is where components usually fail. If everything is flexible, that failure mode is removed. So looking at performance, this is a measured response of a standard microstrip line with our capacitors embedded. So we can see it behaves as a very good DC block. The capacitor is doing its job. Low frequencies in DC are not allowed. And the high frequencies, we're getting a standard line response all the way into millimeter wave bands. Our line is very well matched. It has a standard attenuation relation with frequency. So it shows that we can have a flexible device adding no losses to our system. And in the paper, we did the comparison with a standard off-the-shelf capacitor, which fails upon bending and also adds more losses than the printed device. Now, capacitors have other applications. They're not only used in DC blocking, but they're also very useful in wireless power applications. So we wanted to take an inductive power transfer system and use our capacitor as a tuning element to achieve the resonance and have power transfer around 6.78 or 13.56 megahertz. And the main motivation behind using the printed capacitor was power handling. The slide, what I'm not showing in the slide is the earlier prototype of this system. We used an off-the-shelf ceramic capacitor, which started producing smoke once we put 2 or 3 watts into it. It didn't have the right power handling. It didn't have the right thermal properties. And it wasn't simply a suitable choice, even from a pure thermal point of view, ignoring any flexibility considerations. So here you can see the printed coils. The tuning capacitor is now embedded within the first turn of the coil. So we effectively turn the entire first turn of the coil into a capacitor. You can see the rectifier integrated with the same substrate, and the application is a printed wearable heater. And here you can see the thermal photograph of the system. The coils are reasonably cool because they're low resistance. You can see the capacitor, there's slightly higher increase in temperature because the dielectric loss in the capacitor itself. And you can actually see the warmest part of the system is the rectifier. So the diodes themselves, because they're quite resistive and they're quite small, they're generating significant heat, and they might be a failure point in the system. For the application and for the system that we're building, this was acceptable. And we can see the heater doing its job, heating our power and receiving the power efficiently from our power conversion system. So how does this system operate? We can see it's quite efficient. We can receive over 15 watts at 6 megahertz converted to DC using all flexible electronics. State of the art was about 10 times lower than that, around 1 watt. So it shows that just by making substitutions, choosing thermally optimal materials and thermally optimal devices, we can achieve both high efficiency and high power handling. And we need to remember that we can outperform rigid components using flexible parts, if not in terms of losses or operation frequencies, then at least in terms of thermal, given appropriate design and given the right application. This also allowed us to build other applications. So instead of a printed coil, we built an embroidered coil, which we integrated within a smart bandage. And the smart bandage basically uses ultraviolet, converted from the electrical input, to kill bacteria within a wound, have full digital control on the ultraviolet so that we can control the intensity, potentially mitigating any risk of cancer, while still providing the antibacterial effect of UV. Here is an implementation. The circuit is using standard polyamide and Kapton, integrated within a bandage. Coils are embroidered within the bandage, and you can see the functional part, which is the LEDs encapsulated using polyurethane with small openings around where the light is being emitted to make sure the UVC is not getting absorbed. In terms of efficiency and operation range, it works over several centimeters. Again, another demonstration why we need multiple watts whilst power transfer in the body, and why we need to do so in a safe and efficient way using large area electronics in wearable applications. Everything I've talked about so far was physically building wireless systems on flexible circuits, but we found that some of our structures have translated into learning experience, and I think this is one of the main interesting parts of working on flexible and wearable RF circuits, is that trying to build a low-loss transmission line structure in textiles using surface waves was not any different from our point of view from building a similar structure 100 times smaller at a higher frequency on an integrated chip, trying to minimize losses at terahertz applications. So all I'm trying to say here is, even though flexible RF electronics might not have an immediate application in the next 1 or 2 years, they will teach us valuable information about building higher frequency systems which are immediately relevant in commercial communication or networking applications. The last part of my talk is around sustainability. So I've mentioned that these systems should be sustainable. So we've got some numbers and some materials to back this up and to try and explain what we're doing in terms of design and fabrication to have sustainable electronics. One of it is material choices. So we can take materials like carbon, print that carbon using standard screen printing with IPA spray. On a standard fabric, we can then have a nice thin or thick layer of activated carbon. Activated carbon is an industrial or agricultural waste, so it's a material that's abundantly available. And when built in millimeter thicknesses, it can give us 1 to 5 ohm sheet resistance suitable for RF applications. And here you can see a photograph of a fabric antenna, patch antenna that was fabricated using all carbon conductors. And we can see a good agreement between the standard modeling and the measurements when it comes to a wearable antenna made out of a low conductivity material, radiation efficiency with around 30%. So not ideal, but for a non-metal conductor, it's sufficient for most wearable applications. Now, another point is not just about changing the materials to potentially biodegradable or bio-based materials, but also recycling. So when we're looking at PCBs, one of the problems is that FR4 is extremely cheap, but it's not sustainable. So if you want an alternative, you want something that could be as cheap and as robust from a dielectric point of view, and that's where we turn to industrial waste, which is recycled steel. We basically get a steel sample, we coat it with a nanometer thick dielectric, silicon dioxide, and then we print our traces on top of that circuit using standard additive manufacturing. And if we want to recycle the inks or recycle the substrate, then everything is ultrasonicated in a water bath. Your components are now afloat. You can collect the ICs and reuse them. Your silver probably will get disposed, but that's something we're exploring. But most importantly, your dielectric is intact. It's a steel substrate, so it's not going to be destroyed. You can then reuse it on a new circuit and get the same performance. The RF engineers in the room probably think it's a terrible idea to put a PCB on metal because you get too much capacitance and very thin dielectric, which is why we struggled with trying to put an antenna. You can't put a transmission line on the substrate, it's too capacitive. You can't put an antenna, all the radiation will be absorbed into a substrate. So we decided to make use of the vertical direction, and we started building monopoles. So we 3D printed scaffolds out of PLA, biodegradable. We coated them with silver, so a very basic fabrication approach, but it gave us very good antenna performance, and it allowed us to have a familiar structure of monopole antennas on metal-based substrates fabricated using industrial waste in a fully recyclable or biodegradable process. Behaves like a normal antenna. We can synthesize broadband antennas using the structure. We can get wide gain band and wide gain mesh. So everything that we're looking for in terms of communication performance. In terms of life cycle assessment, how much improvement does this have from an environmental point of view? Here is the FR4 PCB. Moving to a steel PCB is not good on its own, but once you start to recycle your component, you're significantly reducing the carbon footprint of the system. And once you recover all the ICs you've put into the circuit, then you're significantly reducing the carbon footprint of your system. Another thing about carbon, these are pictures of RFICs. And one thing you notice over those RFICs is the large area consumed by inductors and matching networks. Unfortunately, the smaller we go with the IC process and the more advanced our semiconductor node is, the higher the equivalent carbon emissions in that system. So it means we should try and find alternatives in the old processes. And unfortunately, as we're going higher in frequency, we can see a trend that we are using less and less sustainable, but more high-performing CMOS architectures. So ultimately, we need to find a trade-off in the middle where we consider also the carbon footprint of the CMOS process alongside the promised performance in terms of frequency and gain. We have a paper that will be out as a preprint on this topic, where we did a life cycle assessment of every possible microwave component, PCBs and ICs, and explored what design trade-offs a designer could consider to improve the sustainability of our system. It's not online yet, but it should be in a few days. So please get in touch if you want a copy. So just before I finish, invitation to work with us. We like to build things on new materials. We have fabrication facilities. So if you're developing any new conductors or materials, we would love to take samples and characterize them, for example, high frequency, in antenna application, or in on-wafer device applications. So it's an open invitation to anyone who builds material to get in touch. And finally, just saying that most RF electronics could be made using large area systems. We've seen good examples in sensing and in power transfer. We've seen examples of recycling, and finally, where translating the learning from flexible electronics could benefit the standard RF electronics. So thank you for listening, and I'm happy to take questions.